Hello, everybody. Thanks for being here, and thanks for letting me be here. My talk is called Locking the Throne Room, and one word of warning, this is not the first time I'm giving a talk with this name. This is actually the nth time, but this talk is pretty fresh. It's actually very fresh. I just finished the last slides 5 minutes ago. So this is this is an extended version of following a talk which was touching some theory on things and having now some practice and some evaluation. So you might be liking it. About myself, my name is Mari Heydrich. I'm a researcher at the Ruhr University in Bochum. I work for other companies in Germany doing client-side security pen testing. I'm a published author, created the HTML5 security cheat sheet, initiated the PHP RDS project, and I'm on Twitter. That's it. So the next 50 slides are not gonna be having too many numbers and bar charts, but they're gonna be quite tough. So take a deep breath. There's a lot of code, there's a lot of research results, and a lot of interesting thoughts I hope to be able to see in your heads, and let's see where we end up with. Today's menu, we're gonna talk about JavaScript, we're gonna talk about the DOM a little bit, and in general about cross-site scripting. Now, cross-site scripting might sound boring, has been covered by a large body of research, but we try to find a new angle and have a look at it, and especially have a look at fixing cross-site scripting. So we're not only going to have a look at cross-site scripting itself, so we're also going to see the current mitigation approaches. We're going to see how servers and how browsers are going to try to fix cross-site scripting, and we're going to have a look in the petri dishes of current development. And afterwards, we're going to see a slightly different approach of kind of getting hands on cross-site scripting, of attempting to fix it, and we're going to find a way to reason why this is necessary and what went wrong during the last 10 years. But first of all, some theory, and then we're going to see some horrific reality, and then we're going to talk about some future work, and that's going to be it then. So JavaScript and XSS. When we talk about cross-site scripting or about XSS, we should remember what it really is or where it really came from. Like back then, when it was kind of first time documented, it was about two sites scripting each other. It was in the terms of iframes, when there was a possibility for one frame to just access data from the other frame. And this has been made impossible by the SOP, and there were breaches then and when. But what we see as cross-site scripting today is not really cross-site scripting, because usually there are not two sites scripting each other. It's just a markup injection, a JavaScript injection, a plug-in code injection, stuff like that. But we're still going to stick to this term just for simplicity's sake. The first published attacks covering cross-site scripting were coming from the late 90s. Some people I heard were already playing with that stuff in the early and mid 90s. So these things have been around for quite some time, like more than 10 years. Meanwhile, we talk about 3 of even 4 major variations of cross-site scripting. The first one is the most common one, the reflected cross-site scripting. It's just like some parameters being modified. It's going to be reflected in the website, reflected unfiltered, and then we have an alert or something worse. Then we have the persistent cross-site scripting, which is just being stored. We all know it. Then we have the DOM-based cross-site scripting, which is one of my most favorite kinds of cross-site scripting, because it doesn't involve the server. Like the server doesn't see the attack vector, doesn't see the attack payload. And we have plugin-based XSS, which is being carried out by Java applets, by PDFs, by QuickTime movies, and by other plugin-based data, and of course FlashNet, to forget it. And we're going to ask ourselves, what is cross-site scripting for? What's the goal of cross-site scripting? And usually it's around information share theft and modification, and often like the first step of a long following step of other attacks reaching for something higher, which cannot be acquired with cross-site scripting, but initiated with cross-site scripting. So XSS today is still a huge problem. Like we have been dealing with this for like 10 or even 15 years. And we're going to ask ourselves, why is this still a problem? Why is it an ancient attack technique, but we still didn't manage to solve it, just even though it's quite simple when you have a look at it? Well, first of all, it is not simple. It is quite complex, because browsers are very complex tools and have a lot of features and a lot of functionality, and each and every single feature of a browser can usually be used in a cross-site scripting attack or to obfuscate cross-site scripting attacks. We have browser bugs, of course. Every browser is affected by those. We have tons of insecure applications. Jeremiah was telling you about that stuff. We have browser plugins which take control over the browser, have the browser do things that it's not intended to do, take control over various actions the browser could be doing. And we have something very interesting, which is impedance mismatches. So who here could imagine what I mean with impedance mismatches in terms of cross-site scripting? I don't see a hand, which is a good sign, because then we're going to have some nice demos later on. Impedance mismatches basically means something is coming in, and the server will say, well, this is looking okay, and something is coming out, and the browser says, like, well, this is not okay, I'm just going to execute some JavaScript. And this happens surprisingly often. We're going to see 1 or 2 older examples of those. We have a lot of application layer mitigation concepts, like we have the browser-side XSS filters, we have server-side XSS filters, we have protection layers such as mod security, stuff working in the server as a server extension, we have proxies in doing things, and all these solutions that exist so far work on their layer, but don't really work on the layer where the stuff is happening. And in my opinion, and I might be completely wrong with that, and please correct me if I am, XSS is a user agent problem. I'm not saying it's a browser problem, I'm saying it's a user agent problem. So there are other user agents, browser-like applications, such as, for example, an email client, or an IM client, or a Skype, or other software, which is acting like a browser, rendering and parsing HTML, but it's not really a browser, but still affected by cross-site scripting. But in the end, it's not a server problem, it's not a network problem, it's not a database problem, it's definitely a browser or user agent problem. So let's have a look at the mitigation history. What have developers and vendors been doing to fight XSS so far in the last 15 years? Well, there's a lot of stuff going on the server side. And for example, if you have a look at languages such as PHP, there is native runtime functions. And one of my favorite functions doing basic XSS protection is actually striptex. Who here knows striptex and what striptex is doing? No one knows striptex? No PHP developer here? It's kind of a good sign, I guess. Striptex is pretty awesome because striptex just strips text, like it's a speaking name. It just checks, is there something HTML-ish, HTML-ish in my document or in my string? If there is something, I just throw it out. And it's very rigid. And at some point, developers were saying, like, well, striptex is a little bit too harsh because some kind of HTML we want to allow, and some kind of HTML we don't. So, for example, people were saying, like, we want to have a profile for our users, and they should be able to make text bold. And so the B tag should be allowed, but all other tags should not be allowed. And then striptex, or the PHP developers went along and said, like, okay, well, you're going to get a second parameter. And in the second parameter, you can add allowed tags, and you can just use them as a string, which is comma separated. So if you want to allow B and A, you just make B, comma A, which is a crazy idea because they completely forgot about attribute handlers or about event handlers, and then again, of course, enabled XSS. So striptex is rather stupid and should not be used. A different approach would be to use HTML entities, which is converting all that looks like HTML into the respecting entities. So no information is lost, but it's not going to be rendered by the browser. But those of you who followed the talk yesterday saw that in some situations HTML entities doesn't help you at all. And of course, if you want to allow the user to use HTML on the website, on the profile and something or whatever it is, then HTML entities cannot be used. So there must be some kind of solution which is capable of telling apart the bad and the good HTML. Therefore, we have external libraries filtering input and output. One of the most common libraries on the PHP market is HTML Purifier. And this is an extremely powerful tool. HTML Purifier has been around for many years, and it's actually extremely complex. I think it's consisting of more than 12,000 lines of code, and it's taking an input string, completely taking it apart, building a markup tree, a DOM tree with an internal parser and lexer, going through the nodes of the tree and reassembling another string, and then sending that string out, which is then being sanitized. And it's extremely hard to break HTML Purify because of this grammar-supported approach. On the other hand, for Java people, we have anti-semi, which is doing a similarly good job. We have cases, which is a crap solution. We have anti-XSS, which is a quite good solution. We have safe HTML, which is a quite good solution. And we have interesting other and different mitigation possibilities, for example, to use the yesterday mentioned HTTP-only cookies invented or invoked in 2008, making sure that an XSS attack, for example, cannot access document cookie. Only HTTP requests can access document cookie. I would say from an attacker perspective that a web application is like a nice picnic basket. So you don't necessarily want to have document cookie. There's so many more attractive things rather than document cookie. But well, we have client-side XSS protection attempts as well. We have two-static HTML, which is a proprietary function in IE 8+, so also newer IE versions. We have two-static HTML available when you use Firefox in combination with NoScript, but it's doing something completely different. We have the IE 8+ XSS filter. We have the WebKit XSS auditor, which is basically doing the same. Like they have a look at input strings coming in by the URL, match that stuff against the rendered content, and if they find out that there is a match, and this match is also be found on the blacklist, then script execution is being blocked, or the stuff is being diffused, which the filter considers to be bad. We have protective extensions such as NoScript. There's also not scripts for Chrome, but I wouldn't use it if I were you. And we have interesting upcoming approaches such as CSP, which is called Content Security Policy, and providing developers a possibility to give a rather fine-grained policy for the website to tell the browser which parts of the site can contain JavaScript, how it can look, what methods are missing or cannot be used, like eval methods or function prototype and stuff like that. But it's still in its very beginnings, and I think some recent studies showed that most developers are still using it wrong. But it's there and it can be used. Well, the reliability of server-side XSS filters, I would judge it as so-so. And I just gotta admit that we broke every single one of these server-side XSS filters. We broke anti-semi, we broke the HTML purifier, and we broke several other ones, and we really enjoyed it. Now I want to show you how we broke it and what we can derive from this breaking and what the actual outcome of these years of research against server-side filters was. Let's get back to the impedance mismatch. In essence, impedance mismatch means that layer A is unaware of what layer B is doing, but still attempts to control the data for layer B. That means, for example, if the server is attempting to protect the client from getting malicious markup, which is executing code or whatever, but has no idea what the client is actually capable of, then it's going to be a little bit complicated. And this vector you can see here, let me just try to hover it without leaving the presentation. This was one vector we once analyzed. It's fixed for a long time, but which we once found and analyzed and tested with HTML purifier, and it's caused a bypass of HTML purifier. Can someone here tell me what was the critical character in this very vector? So we have a link, and we have a style attribute, and the style attribute is getting a background property, and the background property is getting the URL value, which is filled with a quoted string, which is starting here. Then correctly escaped, moving on with some code in here, but still correctly escaped, we're not breaking out. Moving on, still correctly escaped. And the string ends, the final quote, the semicolon ends the property, the double quote ends the attribute, and this is ending the tag. So what is actually wrong with this example? Who can spot it? Well, the critical character here is actually the exclamation mark. In rather early versions of a commonly used browser, we had the problem that the exclamation mark showed to be a delimiter for actually correctly quoted strings. The assumption was that due to the fact that CSS supports a property or an additional attribute which is called exclamation mark important, that the parser was jumping there, seeing like, oh, there's an exclamation mark. There could be an important afterwards. No, there is none, so let's just back and get to the next property. So since the HTML purifier could not know about this capability, it could not protect against this. So this was a valid bypass. And of this type of bypass exists in a lot of server-side filter libraries. Like you have a feature in your browser, and the server-side filtering library does not know the feature and cannot know it. Sometimes it's a feature, sometimes it's a bug, and sometimes it's just weird. Here's another example, which I think I published some 1.5 years ago. And this is a mildly obfuscated HTML vector. Who can tell me what it's actually doing? Well, it's quite easy to find out if you just have a look at the code. So here we have some garbage, and then we start a processing instruction, we end it. And this is actually an L, so we start an L tag, which does not exist, but we do not care. Then we have some Unicode here, some garbage again. Oh, there's a style attribute. Inside the style attribute, we have a behavior. This behavior is pointing to the string default time 2, which is an ancient behavior once kind of predecessing the SVG standard and taking care of HTML elements being animatable. Then we have an onBegin event handler, which is pointing to a heavily obfuscated JavaScript string, which is basically saying alert parenthesis 1 parenthesis closing, and that's it. So it's doing nothing more than alert 1. But your server-side filter or your server-side firewall or WAF or however you might call it might have some trouble with processing this data, whereas the user agent doesn't, because he knows these features, he knows this ancient stuff, and is able to parse those. You can try it out if you want, so the link is here. It's still prepared for you to just play with it. And we have further vectors that are generating hard headaches for server-side XSS filters. First of all, it's of course plugin-based XSS. So how is the server supposed to know if a plugin, which is compressed or obfuscated or doing other stuff, but has the possibility of accessing the website's DOM? How is the server going to know if there is some obfuscated JavaScript in there? Well, effectively, the server cannot know us because the server would have to be able to completely parse the plugin, have a look into it, evade possible detection techniques. The malware guys here should know that. And there is no way for the server to find out if plugin content or anything comparable is malicious or not. And this is the problem for Adobe PDFs. This is a problem for Java applets, and we're going to see some examples about that later on. This is a problem with Flash. This is a problem with QuickTime videos. Also, QuickTime videos can execute JavaScript. And as you saw yesterday, or some of you saw yesterday, this is a problem with SVG images as well. And there is more problems server-side XSS filters are actually facing. And one of these is, for example, char set injections and content sniffing. So if you have a website which is running in, let's say, UTF-8, or not especially equipped with a char set, such as UTF-8 or whatever you want to choose, and you introduce some text or some input which is encoded in UTF-7, like how is the browser going to be able to decide what to choose now for a char set? If, for example, there is some text which is not applied with the char set and some huge incoming data which is encoded in UTF-7, then the browser might be thinking, well, so there's UTF-7, which is the major content of the website, so let's just put it all in UTF-7. Which effectively means that you have the possibility of deploying a vector which doesn't look like HTML at all because it doesn't use these lesser thans and greater thans. Same as, for example, for EBC, DIC, or AppStick, which is, I think, I'm just way too young to know these things, an old IBA mainframe char set, which is still around in some user agents. We also have, for example, the series of Mac char sets, Mac Farsi. And if I remember correctly, Hasekawa Yuzuka once found a nice XSS vector working in Firefox, completely encoded in Mac Farsi. And this is just such a beautiful vector, so I found it and want to show it to you. Here's this fella. So if you go along and tell the website via an injection, hey, website, just be encoded in XMac Farsi, and then we have the sun, and then we have script, then we have the moon, then we have alert 1. You could show this vector to your girlfriend/boyfriend if you feel like, because it's very romantic. We again have the sun. We again have the sun, then we again have the moon. And this is awesome. This worked in Firefox. Can you believe it? Like, this worked. This alerted 1. So you can see this is quite of a tough task for a server-side filter to find out that the star, or that the sun and the moon is actually representing the lesser than and the greater than and the HTML control characters. Well, some years ago, there was also the possibility to hide XSS data in images. So people were uploading images, leaving away the extension, and then the browser wasn't really sure, oh, what should I do with it? Is it now like a GIF, or is it some other stuff? I cannot really determine. And then some browsers actually switched to treating the whole thing as HTML, and again, executing JavaScript, and the server had a few possibilities to actually notice that. Then we had chameleon files. Yesterday we heard about the GIFRs. We have cross-context scripting attacks where, for example, the browser is attacking Skype, or Skype is attacking the browser, or some other instant messaging tools. We have the possibility to trigger XSS from within OpenOffice documents. We can open the browser or the default browser from within OpenOffice documents, even local files on your hard disk and stuff like that. So XSS is quite big and quite complex. And we still have DOM XSS, where the server doesn't even see the attack and doesn't even see the payload. So the quintessence so far is that approaching XSS with server-side filters is kind of a little bit wrong. Like, do you see the flaw of trying so, and trying so for 15 years meanwhile? It is quite nice in some situations. Maybe we can even say it's quite nice in the majority of situations. But to really protect against XSS, we should not rely on the server. The server is affected by char sets. The server is affected by impedance mismatches. And I think I have another nice example for this. Let me just show you this little tool. For those who don't know the tool yet, this is just basically a tool which is accepting infront from mine, rendering it, and then taking the inner HTML property of the rendered input, showing it in this tag box to just show me what the browser is internally doing with the markup. And I prepared the string for you, which is hello, and we have a strike tag, so you see it's struck. And then we go along and have a look what we can see here. So this is what I entered. Like, we have a lowercase s, and the result is an uppercase s. Well, sure, HTML4 is uppercase, so the browser is nice and transforms it for us because it would be more correct. But if we go along, say, for example, we have a class, and we say like hello. So we have an empty class, and the empty class is being left away. So this is the first mismatch between what's actually there and what's used by the browser, because empty class is redundant, we don't need it, so throw away the empty class. Let's parse faster, performance is awesome. So we put something in that class and say, like, again, hello, and what can you see? You can see there are no quotes anymore. The quotes are gone. We were nice developers. We added quotes. No quotes here. So we think like, okay, if there are no quotes, does this already mean we have an attack when we just enter, for example, some white space? And in that second, in that moment we enter the white space, you can see the quotes reappear. Now they're suddenly there. And you might think, okay, if you take the whole thing and quote it with single quotes, would that make a difference? Whoops. Say again, hello. No quotes here. We add some white space, and whoops, they disappear. And they even normalize to be double quotes again. So the browser is doing a lot of stuff, and this is done by almost every single browser. I think the only browser not doing things like this is Opera, but they do other stuff. So we learned that. So we might think, okay, how can you actually turn this into an attack? And luckily, this stuff is fixed, and it has been documented, I think, since 2007. So it is not around anymore, but it was, and it caused some trouble. Like, have a look, for example, if we use another attribute delimiter, which is the backtick. Now we have this, oopsie, and we move along and remove the white space, and suddenly we have S, class, then we have an empty class, and all of a sudden we have an hello attribute. So if we want to actually abuse this, let me show you, img, and for example, alt. Let's make it really nice, really standards conform. So the server-side filter will definitely leave it through and let it pass. And say, for example, on error equals equals alert 1. Let's close this. Give the whole thing a source. So there's going to be an error event. Maybe source with a C. And yeah, you can see that we have an alert. This is completely clean and proper markup. Every server-side filter would say, well, this is all right. We have the source, which is correctly quoted. We have the alt attribute, which is correctly quoted. What should go wrong? Only on inner HTML access, this will transform. And there is another funny example, which is documented on the HTML5 cheat sheet as well, which I can present here, which is for unknown tags. Let's have a look at this fellow. We have an X tag, which is empty. Does anyone see the X tag down here? I don't see it, so it doesn't seem to be here. Let's enter some text into this X tag, 1, 2, 3. We can see the 1, 2, 3 is there, and the closing X is there as well. But what about the starting X? It's gone. So let's add a 0. Suddenly it appears. So there is some fishy going on. And we'll think now, okay, we have an unknown tag. The user agent is not really sure what to do with this. Let's give it a namespace and tell it what to do. XMLNS. Let's have it be empty. And everything's so far all right. We have the 0, we have the X, we have the space, we have the XMLNS, we have the empty namespace, we have the content, we have the closing tag. But what would possibly happen if I write something into this namespace? Does anyone have an idea? Except for some few people who already saw the example that we offer. So anyone has any idea what's going to happen if I enter some text into this namespace? Well, let's find out. Suddenly, this whole thing explodes. You can see a huge processing instructions coming. I'm saying like XML namespace prefix default XNS equals X, closing itself, then having the proper X tag, having the proper XML and S. It's all still lowercase, so it's transforming itself to lowercase. Then having the namespace itself, having the content, closing the tag, and everything's fine. So who here sees how we could possibly exploit that? No idea? Okay, let's have a look. So what we can do is analyze what happens to the namespace data. We can see here YYY. We can see here YYY. This is correctly quoted. This isn't. This is just there. So why don't we just close the tag? So suddenly we close the processing instruction, and we say S, and you can see it struck. So we just broke out inside the attribute. And we can, of course, continue and say img srac equals X on error equals alert. Oh, there we go already. Doesn't give me the chance to enter the 1. All right. And again, you can see we have completely correct markup. But what's happening afterwards by being treated by the client is making it, it's just kind of armorizing it. And this is usually not known by developers. This is usually not known by WAF vendors. And this is usually not bound by server-side filters. Well, some do meanwhile. But you can see the problem of impedance mismatches. Well, we have DOM XSS, we have impedance mismatches, we have plugin XSS. we have so many situations where the server is completely helpless against XSS attacks. And we have to think, okay, well, no wonder XSS is still around if we don't have any proper protection against this. So the server is it just cannot serve protection anymore. And we also have to think, for example, where will the server be in 5 years? Like, what's going to happen with classic client-server architectures? Are they still going to be around? Is this going to be more cloudy, or do we have more local HTML files? Do we have offline HTML files or offline websites which we are going to use? Where is the server then? Even if it could protect us, where would it be then? So, to kind of approach the problem, we might actually want to revisit XSS. And what is XSS? What is it doing? Like, most importantly, XSS attacks target the client, nothing else, just the client. Initially, it's always and just the client. XSS attacks are being executed client-side, so again, client. XSS attacks aim for client-side data and client-side control, again, the client. XSS attacks impersonate the user then and when, who is sitting in front of the client. So XSS is essentially a client-side problem and nothing else. Sometimes, of course, XSS is being caused by server-side vulnerabilities, but in the most situations, it's caused by client-side or affecting the client or targeting something on the client. But still, we try to improve our server-side filters. We try to protect against XSS with the server. So again, there's a massive mismatch. Our idea was now, why not just try to teach the client to protect itself against XSS? And to just go a particular way, saying we give or we take some of the client's capability and add some more features to the client to make the client aware of what's going to happen. If there is a script execution, can we have the client learn that there is a script execution and how to deal with it? And the approach was a little bit inspired by HTTP only, because it was already taking away some client capabilities. But this was only affecting the cookies. And we want to protect more than only the cookies. We want to protect, for example, CSRF tokens. We want to protect form URIs or form actions. There are so many interesting things in the client to protect. And we thought about a way to actually accomplish that. And JavaScript up to 1.5 kind of enabled this. Unfortunately, the way we found back then, we were working on this field for quite some time, was non-standard and actually a pretty crappy way. But I'm still nevertheless going to show you what we did back then. We used a proprietary feature called defineGetter, or to be precise, __defineGetter__. This gave us the possibility to take an arbitrary piece of script and say, like, for example, we have document, and document has the method defineGetter. It really has in Firefox and other browsers, so have a look at that. And we want to define the getter for document's property cookie. So this is the parent object, this is defineGetter, this is the child object to define the getter for, and this is the reaction to be triggered once someone tries to get document cookie. So if now the attacker goes along and does some standard XSS trickery in doing like alert document cookie, you all saw these vector numerous times, I guess, then document cookie is not going to be alerted, but the getter is being called, and what happens is another alert saying no cookie access, return false, so no access to the cookies. Quite nice, we can block cookie access in JavaScript, or can we? Of course, no we can't. First of all, it's proprietary, so it's really, really bad to use. It's not tamper resistant at all, because an attacker could just detect that this protection is in place and just switch it off. So what is it used for? What's it useful for? Nothing. In the end, we learned after some time this is nice for some experiments, but not really valid for actually protecting object getters or setting object getters or protecting object properties inside the DOM. The attack is quite easy to construct. Like, there are numerous attacks against this, but this is the easiest one. Again, we have the protective code here. We say no document, defineGetter, cookie functional, and cookie, and so on and so on. And what the attacker does right now is first detecting, oh, this dude is protecting his cookie, so let's do something here. Let's just call the delete operator, say delete document cookie, then alert document cookie. And guess what? This is going to be the proper cookie value. So invalid protection. Doesn't work at all. But it was a nice try. And what we were searching for afterwards was, of course, a way to find, first of all, a certain tamper resistance. Like, how could we make sure that an attacker is not capable of just deleting our protection again? Because this really sucks. And we tried further ways to actually attack our approach. We tried further ways to improve our approach. And we ended up with using document __proto __ defineGetter. Went deeper and deeper in the DOM chain. We used the document constructor and its prototype and tried various eccentric ways of just protecting that thing and outsourcing the problem, but nothing really worked. All attempts we undertook to protect the client or to protect DOM properties were completely doomed. And at some point, we realized that JavaScript 1.8 is so far completely unsuitable of delivering DOM-based XSS protection. But there was a light, and this light was called ECMAScript 5. Who here has already worked with ECMAScript 5? Awesome. One hand. Oh, this is going to be tough. Oh, two hands. This is going to be tough. Anyway, so the older user agents, such as Firefox 3, Internet Explorer 8, and Opera 11, which is not really old, but well, it's Opera, they are based on ECMAScript 3, which is not giving us any possibility to do the nice we want to do. But the modern user agents come with ECMAScript 5 compliance. This includes Internet Explorer 9 and, of course, 10. This includes Firefox 4 Plus, Safari 5 Plus, although it's hopelessly buggy, and Google Chrome. So there is a lot of novelties in ECMAScript 5, but the most relevant and interesting novelties in this thing is some object extensions. And these object extensions are object freeze, object seal, object define properties, super important for us, or the alias object define properties for pluralized property definition, and the very interesting and very verbose method get on property names. We're going to talk about this one later. This one is first define property. We have other interesting things like proxy objects, but we cannot really use them because they are not allowed for host objects, so we cannot protect document. We have more meta-programming APIs, and we have nice ways of combining the whole stuff with DOM level 3 events. But the most important thing here on this slide is actually object-defined property. Let's see why this is. Object-defined property is pretty awesome. It accepts 3 parameters, not very much unlike define getter or define setter. The first parameter is the parent object to be called on. The second The second parameter is the child object to define, which is passed in as a string. And the third parameter is very interesting because it's a descriptor literal. And this descriptor literal allows us to define a lot of things for this very property. We can, for example, define the get and the set behavior in a standards conform way, not unlike the define getter and define setter functionality. We can also redefine the value. We can control the enumerability, so if it's visible in a for-in loop. We can set the writability, so if it's read-only or read-write. And we can set the configurability. And the configurability is the most important property here. Let me show you an example. This is doing basically the same as our hopeless approach with the define getter. We have a call to object define property. We pass in document as first parameter, the parent object. We pass in cookie as a string to define what the child object to redefine is. And then we pass in the descriptor literal. What we do is we redefine the getter. So we make sure that a getter access to document cookie is going to be resulting in a return false. We redefine the setter, so if someone tries to set document cookie, like in some situations this could be interesting, it's again returning false, so there is no setter access possible. And then we seal the whole thing by configurable false. So we make sure that no one else can ever touch this getter-setter modification. So this is final, this is tamper resistant. If now the attacker goes along and says like delete document cookie, tries to alert document cookie, what is going to happen? He's going to get a false, no document cookie. So this is quite awesome. We can finally set DOM objects to a final state if we do it right. So the good thing with configurable false is that it's even stronger than delete, and we tried a long time to pen test it or to find ways around it. And there are some, but they are fixable, or we fixed them, and they were depending on the implementation. So in the end, configurable false means a final state for this object. A redefinition is not possible, only on Safari, but this is a bug. This is, of course, quite awesome, but it implies a little bit of a philosophical problem, because the developer with a benign mind can, of course, set objects to a final state, but the attacker could theoretically too. So it's a little bit about the order of deployment here. So who deploys first can set objects to a final state. This is one important bit of knowledge we should draw from ECMAScript 5. And we're going to see ways around that later on. So what we can do right now is we can regulate access in general. We can say you can access this property or you can't. We can even find out who is trying to access the property, because we have nice properties in JavaScript allowing us to do that. We can, of course, block a whole range of properties. We can just particularly forbid access, but we can also find out if there's a possibility to control access or to monitor access and to find out if it's the right thing to do or if it's a wrong method. Interestingly, we can also, for example, go along and protect forms. Like, forms are a very, very important asset of websites, because a form action, or the value of the form action, depends or takes care where the data the user filled in is going to be sent in. So if you have, for example, a login form and the attacker changes the form action, then the password is gone. That's in plain text. So no one really wants that. So what we're doing here is we grab the form in the DOM. We say document get element by id form. So assuming our form has the id form. Then we again call object define properties, say define form's action, and set this action to our fantasy method IDS underscore detect hijacking. I just thought that out. And the getter action to IDS detect stealing. And again, see this with configurable faults. And the attacker goes along and tries to reset our form action with an XSS. He can't do it anymore, which is quite nice. Of course, there are still ways to do it. This is attackable. This is just an example. But essentially, it demonstrates that we can also protect HTML tags with this technique, or properties of HTML tags. So the first roundup we can conclude to after seeing these examples, we have the possibility to draw a layer of access prohibition inside the DOM. We have the possibility to, for example, implement an IDS because we can check what the values are being passed into function. We can analyze them. We can see if there is a malicious form action being passed in with this detect hijacking or detect stealing method. And we can do a lot of more things. We can even, for example, create a role-based access system right now in the DOM with these strigs. And the good thing here is that a lot of obfuscation methods that might affect the server and its capability of detecting attacks and detecting and blocking XSS attacks do not apply here because the server doesn't really interact with these functionality. It's all happening in the client right when the script is being executed. So there is no obfuscation, there is no impedance mismatches, there is no char set issues because we are right in the moment of script execution and not on the server-side layer or the database layer or any other layer, like for example mod security or below. Bad thing here is it's a blacklist. So we effectively have to know which parts of the website we want to protect. So this is not always the nicest thing. As I mentioned, we can go further. We can create a role-based access control system in pure JavaScript, and it's going to be tough and it's going to be tamper safe. And we can even think about a possibly simple, very simplified protocol. We can say, well, object A is allowed to access document cookie, while object B or method B isn't, and we can enforce that. Let me show you the quick example again with some fantasy methods. Here we have the fantasy method RBAC check setter and the fantasy method IDS check arguments. And if, for example, we have an allowed or a safe getter for document cookie, we can call it my allowed method. We want to grab document cookie. And on access to document cookie, the getter will be called and say like, hey, are you in the range of allowed methods? Are you allowed to do this? If yes, here's document cookie. If no, go to hell. And we can also connect this with the IDS, and the IDS can say like, hey, someone was trying to access cookie, alert, alert, let's send out some kind of log request or whatever you want to do in this situation. When the attacker then goes along and does something bad, says like alert document cookie, the system will notice, hey, alert is not among the allowed methods, so let's better block access and log this as an attack. So we're forcing introspection here. We can give existing properties new capabilities, and we can find out who actually tries to access these properties with, for example, arguments caller. The JavaScripters among you will know what I'm talking about. We can react on these attempts, on these getter and setter attempts, and we can tear up a whole new level of DOM-based protection right in the client. But I'm still talking theory here, and we didn't do an eval yet, so this could all still be bollocks. Let's see what we learned later on. First of all, we decided to make a small case study on this. Excuse me. There is this nice tool out there which is called the SJCL. I always stumble when trying to pronounce this acronym. The Stanford JavaScript Crypto Library, JavaScript Crypto Library, and I did it just again. And it's a nice piece of code because it's providing JavaScript with a lot of crypto stuff. I'm really horrible in crypto stuff. I have no idea about crypto, but people use it and it's known to be safe and proven to be right and whatever. It speaks AES 256 and other things that I have no clue about. And if you think about crypto in the client, you might be like, crypto in the client? That can't be safe. And if you have a look at the website, then the Stanford guys are saying SJCL is secure in the first paragraph on the website. And if you scroll down a little bit and read like the 5th paragraph, they say like, yeah, but not if you have an XSS. So, well, look it out, it's actually there. And of course, this is not true from an XSS perspective. If you have a strong crypto library running in the client, implemented in JavaScript, then the XSS is going to blow this thing apart. You can do anything. You can intercept, you can modify, you can lock keystrokes, whatever you want to do, you can do it with an XSS. XSS is evil. Good thing here, The Stanford JavaScript crypto library is written really badly because it's using global variables. But the good thing is global variables can be very easily protected. So they're kind of hip again. We just go along and say like, hey, global variable, we throw you into our object-defined property. We set you to configurable false so no one can modify you anymore. How's that? And this actually works. Then we have a look at what kind of native methods this library is using. And there are not so many. It uses mathfloor, mathmax, mathrandom, and some other math stuff. It uses document attach event and some native string methods. But that's basically it. We have a handful of methods that are being used by this library. And we can move along and protect every one of these handful of methods. So it's still a little bit blacklisty and still not so nice, but it works. And we can protect this library. But we wanted to seek for another case study. And I think you all know the browser exploitation framework, or called Beef. Like this thing you inject into a website, and then you can do bad stuff like deploy exploits and whatnot. And as seen some minutes ago is actually wrong, because we didn't see it some minutes ago. But again, Beef uses global variables. And I had a talk with a developer of Beef, and actually I asked him on a conference, so if I have a website, and you hack this website, and you inject your Beef, what would possibly stop me as the owner of this website from just being an arse and detecting this kind of injection and saying, no, you inject a global variable in my website. This is called Beef, so I know who you are. And I'm going to change this global variable, and all data you're going to try to steal from me, I'm going to give you back, but modified. And what if this modified data is going to counter Beef you? And I'm going to send you a Beef back to your own Beef. Only thing I would need for this would be a vulnerability in Beef. And it took me an hour to find this vulnerability, and it took me another hour to build the proof of concept, so the Beef was beefed. So he injected a Beef into my website, but I sent the Beef back, used the vulnerability in Beef, and hacked him. Had his geolocation, had everything I needed, and delivered him false data, had his password for the Beef server and everything. And the purpose of the Beef was a little bit, well, not what was desired anymore. The guy maintaining it right now, I think his nickname is Anti-Snitcher. He was not really amused. And he asked me, so what can I do about it? And I said, like, dude, you can't use a global variable. This is not good. So if you want to attack websites, make it right and just seal this global variable so no one can touch your Beef anymore. And he was like, oh. This is a good idea, and he actually protected his Beef, and now it's a little bit better. I don't think, I'm not really sure if it's a good thing I did there, but well, the Beef is safe. So many benefits in ECMAScript 5. The problem with this whole thing is that website owners, if they use such a solution, and we build such a solution, should obey to a new rule, and this is the order of deployment, which is of great importance, because if anyone can deploy before you as a developer, then the whole protection is going to be blown away. Because these objects you're going to be using will be defined propertied already, and this is not so nice. But if you keep this order of deployment, it is very easy to make sure that no one else can use object-defined property. Does anyone of you have an idea how we can stop people from using object-defined property? Well, it's easy. We can just define defined property. So what we do is just we call object-defined property on object-defined property. We say the value is empty, and that's about it. Gone it is forever. So if then someone tries to get along and redefine the setter for example, Windows secret, and set this getter to steal info, it's not going to work because object-defined property is not existing anymore. It's an array and not a function. But well, this is a nice protection against this magic ECMAScript 5 stuff. And we're soon gonna move from the theory to actual evaluation. Just first, let's ask ourselves, where are we right now with ECMAScript 5? Like the good things, we can fully restrict property method access. Like we can do this tamper safe. We have the foundation for a client-side IDS and role-based access control system. And we can completely regulate object access, object extensions. We can even make sure that an object doesn't get new properties or gets other properties taken away, so modification. And the good thing is this plays very well with existing mitigation approaches such as CSP or sandbox iframes. This is a perfect coupling. The contra, it's a blacklist. So we have to know what to protect, and we do not always know that, and we made this experience. And other problems are, for example, magic properties. They cause problems. One of these magic properties is location. Like if you set location in the DOM, there's going to be a redirect, but you can't really set location. It's not a classic variable. And this is causing trouble then and when. Also, we need to prevent the creation of a fresh DOM. Like if you are on the website and you have the possibility to create a fresh DOM, which is not applied with this protection, then the whole protection is gone and the attacker can read document cookie again. And right now, the DOM sucks a little bit because it's so inconsistent, it's so broken. There are so many properties that really need fixing, but each of these bugs is not considered severe enough to actually cause some action on this. But still, we can kind of approach XSS without any obfuscation. We can read and see interesting things, and we can create a meta DOM with some meta programming APIs, and it's quite nice. But enough with the theory already. We wanted to try it out if what we were preaching all the time actually works, and the best thing to try something out is to implement it and to throw it at the community. And that is exactly what we did. So what we did was to publish an overall of 3 completely accessible websites. The first step was we published a website and we enabled attribute injections. So you couldn't inject full tags, but you could control the attributes of existing tags. And we said, hey, community, have a look. And I think there was like 5,000 to 6,000 attempts to break it, and some even succeeded. We're going to see this later on, how this worked. And the second step was a bit more brave, and we said, like, okay, now, since the attribute injection problem was fixed by us and we have it under control, why not allow attackers, why not tear up a website which has no XSS protection at all, like nothing at all? Like the attacker or the challengers could inject anything, script tags, iframes, applets, whatever they wanted. And we did this, and things happened. But the fact is, we published a website with a client-side XSS mitigation approach, and we had no server-side filtering at all. Like every single string was just directly being reflected. What we wanted to do was, of course, to protect it with JavaScript only, and to have a goal we could use here to block access to document cookie. And we implemented a safegetter. So there was the possibility for the benign developer to access document cookie, but not for the attacker. So we also implemented something to make sure that the attacker cannot call the safegetter and abuse it, for example. And we made it extra hard for us because we not only used document cookie, but we also reflected the value of document cookie in the markup inside the script tag with an assignment. So it was extra hard for us. We're going to see the code example soon. And the premise of the challenge was to just say, okay, we announce it, someone breaks it, we fix it, this person gets the score, someone else breaks it again, this person gets the score, we fix it again, and so on. So it was moving, like the target was moving all the time. And we were live fixing what the people were finding, and people were finding things. And it was a tough challenge. But at least we got some extra learning, and let me show you some code examples. Like this was the very first version of the challenge. You don't have to read this whole thing. Important here is that we have a script tag, which is saying document cookie equals something. So we had like double reflected document cookie, first in the headers, then in the website itself. And then an anonymous function, which is calling itself, which is specifying a lot of stuff, giving us some shortcuts to document define property, tearing up a safe event handler, making sure that document cookie is being frozen and set to null, storing it internally, so unreachable from the outside, overwriting some HTML document properties and inner HTML text, content text, and so on to make sure the attacker cannot access this value, and other things. So you can have a look at this code later on if you want to see more details, or just ask me later on, and I can explain. And we also implemented a safegetter, like this one particular method that was allowed to get document cookie, and we call it just safe, and we define safeget. We say, like, okay, we take your arguments, call a caller, we check it, and we check if this was a real event, if the type of the event was a click, if the click was trusted. And if that was the case, a real click and a trusted click coming from a user, we return document cookie. If not, we return null. Looks okay, does it? Looks quite okay. We froze the whole thing so no one could override it or add any new properties. Then we published the challenge and we hoped. Well, and then that happened. In the end, our solution was complete rubbish. And we were taken apart like never before. I think the code was broken an overall of 52 times. People were doing the most interesting, like applying the most interesting attacks. Just a side note, all these attacks are listed. They're publicly available. You can have a look at them and learn from them. And some of them are really, really interesting and showed us features we never knew the browser had. People were spoofing real clicks. People were just saying, okay, then I built my own click and call it like your safe click and set it to is trusted true, and done we are. People were overwriting frozen properties because we did it wrong. People were using iframes with data URIs, creating a fresh DOM. People were using AJAX requests to request the very website and use a regular expression to strip out the value we were hiding. People were finding DOM leaks. People were cloning content into text areas and reading their value. People were doing interesting stuff. The full list is going to be on the page on the next slide. The interesting thing is the code was broken 52 times, and we managed to fix it 52 times. Well, some of these fixes really took us some weeks, but we managed to fix those bugs. In the end, we ended up with a client-side protection library, with a working client-side protection library, which was 70 lines of code, working perfectly well in Internet Explorer 9, working perfectly well in Internet Explorer 10, working so-so in Firefox. Well, not really in Chrome, I'm sorry, and not at all in Opera, but well, maybe someday. But we went somewhere with this. You can have a look at these challenges, and I would appreciate it if you try to break them and increase the number of requests so we can brag with them. The first one is still online. You can find it on html5sec.org/accessesme. This is the one with the attributes. The second one is, of course, still online, which you can find on accessesme.html5sec.org. And this is wrong here. It's supposed to be an L. I'm sorry. html5sec.org. And please have a look. Please break it. So far, we had like 14,000 attempts to break this one, and I think 7,000 to 8,000 attempts to break the first one. And all these vectors that succeeded in breaking it are documented right there. So if you want to have a look at them, feel free. Or if you want to comment them, just drop me a line. In the end, we managed to fix all bypasses, and it was still working. And what we did was use a special trick. Has any one of you ever heard about the object document implementation? Well, this is quite a cool object in JavaScript. We're going to see later on why this is the case. And right now we have the third challenge, which was published, I think, 3 days ago. This is the collaborative approach between Gareth Hayes and me. And so far, there were 8,000 attempts to break it, of which 15 succeeded and 14 were fixed. Like, there's still one remaining, and unfortunately, this is even my bypass based on Java. But well, I think there are some more challenges to come until we can finally prove that it's working, and I think there's still a lot of work to do. But the point was, the ratio is quite good. Oops. Nope. We have 14,000 attempts to break it, with an additional 8,000 attempts to break it, which is more than 20,000 attempts to break it, and only 60 bypasses. And for a completely novel protection mechanism, this is not that bad. So what we were doing to finally protect it against all these 52 bypasses of the second challenge was, I was announcing that, using document interpretation, create HTML document. So the first thing was, of course, to find a way to not have it be so much of a blacklist. So we get them back to this magic function here, which I was mentioning some slides earlier, object get on property names. So sometimes browsers are a little bit non-verbose regarding the properties they know and have. And this is why we had to finally use this abstruse code construct here. We said object get on property names window and concatenate the resulting array with object get on property names uppercase window.prototype. This is giving us an almost full set of browser properties in the window context. Have a look at it. You will see things you never saw before. Constructors, number types, array types that you really do not know that existed. At least it was the case for me. Then we apply a magic trick, which was not our idea. It was actually the idea of Eduardo Vela, and was published in 2006. So what we did was, after the first script tag ended, or right before the first script tag of the website ended, we executed document write plaintext. Can anyone estimate what happens when we write this into the document? Does anyone know what the plaintext tag is? Shall I maybe demonstrate what the plaintext tag is? All right, let's have a look. So if we go ahead and say oops, maybe I should remove the alert. There you go. So nothing really happens. But as you can see, if I add HTML after the plain text, it's not going to be rendered as HTML. It's going to be rendered as plain text. Everything inside this magic plain text tag is plain text. Can we close the plain text tag? No, it's that magic we can't even close it. So This is a very reliable way working in every single browser to make sure that everything, like the whole rest of the document until end of file, is rendered as plain text. There is no HTML going on, no iframes, no applets, nothing. So we can just block the full document from executing or from executing any form of markup, which is nice for us because we are smart and we create an ID which is referencing to that plain text. So all we have to do after adding this plain text is to grab the content of the plain text, take document implementation, execute the method create HTML document, which is creating a shadowed HTML document right in our DOM, throw the whole stuff in, inspect it piece by piece, have a look, oh, we have this tag, we have an iframe, we have this is the following URL, this is the next link, and so on. We can move through all DOM nodes step by step, inspect them as the browser would render them, decide if they are nice or not, throw them out, modify them or leave them as they are, and then later on apply them to the document in a safe and sound way. Thank you. Check the challenge, it's really working. Now we went one step further, or to be precise, Gareth went one step further, and he created JSLR or XSSB3, and this is using all of the above, but he's using some server-side help, because what he's adding is he applies a random ID to any legitimate element. He, for example, utilizes the rendering engine or the template engine of a framework and says like, hey, framework, every single tag you generate for me, give him another ID, which is cryptographically safe, like so. But well, what can we do? It's PHP. Render them out and have the script later on know this ID and check if this element has a valid ID, so render it with everything you need, or it doesn't have the element, or it doesn't have the ID, so inspect it and know this is definitely injected. So we can most definitely tell injected content from legitimate content apart, which is quite interesting in a framework context. This is kind of an extra high security mode for the whole solution. While we're still thriving towards creating a solution which is capable of doing it all on the client, this is like the high security mode. This is what you want for your bank. And again, please try to break it. Have a look at it, try to break it. And as I said, there is one way to break it right now, and this is relating to Java applets. And we hope we can find a fix. We didn't find it so far, but we're working on it. But except from that, there were just few successful attempts, and maybe you'll find one. If you will land on the list of glory, and you will be praised by the others, and shall not be your damage. So we could see JavaScript is capable of protecting us against XSS with some tricks. Still, these tricks are not quite elegant. They're not really nice. Like, you have to know a lot of JavaScript. You have to still act like a blacklist. But the possibilities we have by doing that are immense. We can, for example, just move along and say, OK, we have iframes, and we don't know where these iframes point. So let's just proxy them. Or we can say, well, this website has large images, but I have a small or a slow connection. Let's just proxy those images and compress them on the fly. We can do this with this DOM solution. I think this would be marginally interesting for mobile content providers. We have learned it is feasible, but it's quite fragile and still prone to be broken. But it's a novel and new idea of protecting stuff. And I strongly believe that it's the only idea that can really protect against XSS and all its facets. In the end, we asked ourselves, right now it's fragile, but it's all happening on one layer. And is a fragile approach, being fragile on just one layer, more fragile than a fragile approach on n layers involving server, runtime, database, and whatnot, and WAF and impedance mismatches, HTTP parameter pollution, and whatnot? We think no. There's still a lot of work to be done, and we have a small wish list for browser vendors, and this wish list is actually there to make our approach a little bit more elegant. Future work, we need to fix the DOM. Like, the DOM is right now really broken, and this is the case for almost every browser. We need consistency. Like, in all browsers we tested, events look different. There's always this property is not there, this property is only in this user agent, there it looks like this, there it's set to true, there it's set to 1. This is not consistent. We cannot work with that. We still have DOM black holes. For example, if we assign an anonymous function to an event from any given element on the website, this is not going to be reflected in the DOM. Like, this assignment is just gone. We cannot see it, but it's still there. We can even remove it. We need a higher prio for DOM-based bugs, because future solutions will actually rely on these things. And there is a lot of DOM-based bugs that could be considered as not so severe, but in this context or in future contexts, they actually might be. We need to find time to specify a whitelist-based approach. And actually, I took the time and did it. We're going to see this on the next slide. And we need to fix and refine event handling and the existing DOM properties. We have a nice event which is existing in Firefox only, which is called DOM frame content loaded. This event helped us to control iframes with JavaScript URIs. Major pain. We have DOM level 3 events, which are called DOM sub3 modified. But these events are telling us that something was modified after it was modified. What would be completely awesome would be having an event which is telling us stuff before actual modification happens, so we can judge if the modification is all right and stop it or let it happen. And well, in the end, we finally need a working DOM proxy. Like ECMAScript 7, ECMAScript 6 are on their way of specifying DOM proxies. We have a very early implementation of DOM proxies in Firefox, but it's completely not usable because it's denying its service for host objects and still blacklist. So what we need is a DOM proxy enabling us whitelists. And this is what we're currently specifying. We have been talking to the W3C people, and there might be some progress here. And we have learned that DOM sandboxing kind of works, but it would work nicer if we had, for example, DOM init. Just one event telling us when the DOM is ready, but no JavaScript URI or no iframe has executed that. If we get something like this, we don't need document implementation anymore because we can all do it in the live DOM. We don't need a second DOM anymore. So it's even faster. Also, what would be great would be to have a function or a method called object intercept, where we could just say object intercept window and define all that stuff in there. And if anything is being accessed in window, be it something we know or be it something we don't know, we can see, we can notice it, we can react on it, and we don't need this blacklist anymore. Say protect this, protect this, protect this, and forget this. So the specification is there. There's going to be a publication soon, so hopefully stay tuned. And well, final message here. Please, let's just really fix the Java plugin, because the Java plugin is really pain. What the Java plugin is doing to the browser, this is just not normal. We lose any form of control over the browser. And there is a reason, for example, why for the second challenge we managed to fix all 52 bypasses, and for the third one we didn't. Java is the answer. We cannot do it. Like the way Gareth was creating his DOM is allowing Java applets to just be quicker than that. We cannot win this race if the Java applet or if the Java plugin has that much power. And there has to be something to happen in this direction, because otherwise it's going to be very, very complicated. So we already arrived at the conclusion. So far, XSS in the client remains undefeated, on the server as well, so we're not that bad. But I think a lot of steps in a new direction were made, and we hope that there's a possibility to make more steps in this direction. We all see, and we probably all agree on the fact that rich internet applications gain more complexity, gain more power, gain more impact in our lives. We can see the Windows Developer Preview and the upcoming Windows 8, where these things are going to play a major role. And I strongly believe that client-agnostic server-side XSS filters, or generally filters trying to defeat markup-based attacks, be it XSS or scriptless attacks, are meanwhile kind of designed to fail. They do not know enough, so it is going to be complicated to actually use them and hope that they're doing the best. DOM XSS plugins and so on, we had that. I think it's time for a new approach. We try to specify the first steps of this new approach. We know that there is still a lot of work to be done. But the benefits are quite clear. It's not that super elegant yet, but we have 70 lines of JavaScript code versus 12,091 lines of PHP code compared with, for example, the HTML purifier. I'd say let's get it done. Let's build something in this direction. It's going to be hard. It's going to be complicated. There's going to be a lot of tears, but well, no one said it's going to be easy, so let's see what's going to happen. That was it. I'm out of material. If you have any questions or concerns, I'm pretty sure that there are going to be concerns, then please issue them now or later on a beer. Otherwise, that was it. Thank you.